All right, well, it's recording, so I'm going to go ahead and get started. I'm going to go back into these tabs and find one to do. A big circuit. Yes. Yeah, I can do a really big circuit. Tell you what, why don't I make one up so that it can be plenty complicated? Because these ones that are here, they're all kind of okay. I don't want to say simple because that's kind of relative. But yeah, let me put some in that. Let me do one that's definitely challenging. Oh, and I see. There we go. Thank you for stalling me. Let me get Matthew in. Good morning, Matthew.
Good morning.
Alrighty. So I'm going to draw a circuit and get something out of it. So this is going to have obviously series and parallel, but it's going to have an interesting mix of it. Okay, so let me get to some labeling. I guess we can do R1, R2, or 3, R4, and R5. And let's see, not that I want to make the math any harder than it needs to be, but I guess I can throw some values on here. Let's make this be a 12-volt battery. And as far as these resistances go, I guess we can go just 3K, 5K, 2K, 2K, and I don't know, 4K. Sure. Okay, so I think that this might be a good time to set up that grid like Matthew mentioned yesterday, because I've got 5 resistors. That's a lot to keep track of. So if I were to go R1, R2, R3, R4, R5. Another reason to do this is because if I tried to cram like 15 values onto here, it's going to be a illegible nightmare. So 5 resistors, and now they each will have a resistance, of course. There would be a voltage across them. There would be a current flowing through them, and they should each have some power consumption. Okay, well, this will still be cramped, but at least it'll be more possible to read. So I'll keep coming back to this whenever I can. Okay, so first thing, let's work out the equivalent resistance for this. So if we are looking at things in terms of whether they are in parallel or in series, the way that I'm conceiving of this is, as you come out of this battery, you've got R1, then you've got this thing, and then you've got R5. So 3 things in series, so to speak. So if we're going to get the equivalent resistance for this, really this thing is going to be the trick. So these two are in series with each other, but they are on a parallel branch with R4. In other words, these are both in parallel with that. Now, there's two different ways that I might try and set that up. I want to write them both so I can show you which one is wrong and why it's wrong. If I were to say R2 and R3 are in parallel with R4, it sounds like I might be describing this. 1 over R2 plus 1 over R3 plus 1 over R4. It sounds like I'm saying R2 and R3 are in parallel with R4. See, R2 and R3 are in parallel with R4. However, this does not describe that, because according to this, R2 is also in parallel with R3. That's not true. R2 and R3 are not in parallel, they're in series. So the first thing that you'd actually want to do is combine these to change this into this. Obviously the 2 and 2K are combining to a 4K there. So this would be the time where I would, like, you know, look up for people's facial expressions to see whether they're like, what, or, oh, okay. So you'll have to give me an indication of that in the chat. But these two are the left branch of this parallel, and they are in series together. So they need to add up in series so that I can put them in parallel with this 5K together. So that math is going to look like this. Which would be 1 over 4,000 plus 1 over 5,000. And I'll take that to the calculator and get an answer. Oh, come on. Okay. 1 over. Oops, I didn't do the 1 over. Calculator errors are the best. One over 4,000 plus 1 over 5,000. Okay. Well, that's going to be the resistance of this thing, like that whole thing here. That is going to have an equivalent resistance of, man, that is a lot of 2s. Okay, so if I can, I thought I had some Post-its within reach. Hold on, I've got some Post-it notes here somewhere. I thought I had some Post-it notes. I've gone and lost my Post-it notes. Hold on a second. Let me see if I've got my Post-it notes in the back of the room. Oh, yeah, here we go. This would be a lot easier to do in a whiteboard, but I'll have to stick with this. So this thing, I hereby replace with an equivalent resistor. of 2,222.2. Make sense? So that this whole thing is equivalent to this. So I'm just going to treat it like it. That's special effects right there. Okay, so if that's the case, then I've got 3,000 plus 2,222.2 plus 4,000, and I can actually get an equivalent resistance for this whole thing. So I'm going to go ahead and do that. Plus 3,000 plus 4,000. Okay, the equivalent resistance for this whole circuit is 9,222. Whew! I guess I'll make a note of that. All right then. Now that I've got the total resistance, I've lost my paper now. There we go. Now that I've got the total resistance, I can start using Ohm's law. More special effects. So Ohm's law being V equals IR. We know that the voltage of the whole circuit is 12. And the resistance of the whole circuit is 9,222.2. Now we can get the current for the whole circuit by doing 12 divided by 9,222.2. 12 divided by 9,222.2. Okay, well, we've got 0.0013. I guess that'll be fine. Okay, so that's the current for the whole circuit. At this point, I can actually fill a couple things in to the chart. First of all, I really should have filled in these resistances. So maybe this will stand out better. The resistance of resistor 1 is 3,000. Resistance of resistor 2 is 2,000. Resistor 3 was 2,000. Resistor 4 was 5,000. And resistor 5 is 4,000. Okay. Back one, there you go. Okay, so I just got a current of 0.0013. And the way that works is everything in series will have the same current, which means this has 0.0013, this has 0.0013, and this has 0.0013. Obviously, the trick is this isn't really here, it's actually that, but that just means that these share 0.0013. Anyway, I'll get to that when I get to it. Right now, just do this one. This one has a current of 0.0013. And this has a current of 0.0013. I did not leave enough room for voltage there. Oh well. Right, anyway. Oh well, I'm gonna have to just figure out R5 when I get down there. Since I've got a resistance and a current for resistor 1, we can get a voltage now. Ohm's law, V equals IR. V is unknown. Current is 0.0013, and the resistance 3,000. Just have to multiply those two numbers. Times 3,000. It's 3.9, you guys. See, maybe another color will help it stand out. There we go. So resistor 1 has a resistance of 3,000, a voltage across it of 3.9, and a current through it of 0.0013. The only thing left to calculate is the power consumed. I'm just checking to see if there's anyone waiting in the, okay, we're good. And the power consumed would be 3.9 times 0.0013. That is, power is equal to current times velocity. And so that would be 0.0013 times 3.9. I got 0.00507. Guess I'm alternating colors. Okay, trying to cram all those numbers right here. Yeah, that'll just be a lost cause. Okay, let's deal with this now. What is the voltage across this? So remember, the current for the whole circuit is 0.0013 amps, which means it's 0.0013 amps through this and 0.0013 amps through this. Even though this is a fictional resistor, it represents something real, and they would have the same current through them, 0.0013. So I can still find the voltage across this resistor, and it would be the same as the voltage across that. So let's do that. I've got, this fictional resistor here, whose resistance is 2,222.2. And the current going through this little bit of the circuit is 0.0013. So putting those values into Ohm's law, just have to multiply them together to get V. That's going to be 2222.2 times 0.01. Oh, sorry, not enough zeros. Darn it. 0.0013. There we go. Oh, I wish this calculator just had like a backspace button. I have to start over whenever I make a mistake. Okay, so it's 2.8 repeating. So I guess I'll just call it 2.89. Yeah, that's the appropriate amount of lazy. Okay, so 2.89 volts across this. Well, that's 2.89 volts across this side and 2.89 volts across this side. Okay, so I know the voltage across R4 then. It's 2.89. But what about the voltage across these two? In this particular case, just knowing that R2 and R3 have to be able to spend 2.89 volts, I can kind of just imagine that it is in this circuit. With a 2.89 volt battery, and then I've got R2 and R3. How would I do it in that case? Well, I could just do Ohm's law, but in this particular case, I actually do have a shortcut. I don't like to do a shortcut that ends up not teaching you something. However, I'm just doing this, which is a very basic circuit. So I think that you would be able to do this one. So I'm going to go ahead and use the shortcut. These two resistors are the same, which means this one's going to take half the voltage and that one's going to take half the voltage. So I can just divide 2.89 into 2. Oops, that's a plus. Okay, so 1.4. All right, so 2.89 volts across here. That would be 1.4 volts here and 1.4 volts here. Okay, how about that current? Once again, Ohm's law will give us the current because we've got a bunch of V's and R's. So let me just save a little bit of time. If V equals IR and I'm looking for I could just divide both sides by R. So current is going to be voltage divided by resistance. Hey, your camera, get in focus, why don't you? It's like focus up there. There you go. So if I just do V divided by R, I should get a current. So I'll do that for each of them. 1.4 divided by 2,000. Is really small. It's 0.00072. And of course, you get the same answer here. All right, this one will be different. 2.89 times, I'm sorry, divided by 5,000. Oops. 2.89 divided by 5,000. 0.000578. Holy cow. Well, hey, look, I've got a whole bunch of V's and I's. If power is equal to current times voltage, if P equals IV, then I can just get this by multiplying those two numbers. Go ahead and do all those. 1.4 times 0.00072. Sheesh. Oh, I didn't put enough zeros in there. There we go. Fixed it. Man. 1.4 times 0.00072. Hey, it's the same. Oh, duh. Why did I do that calculation? It's the same numbers. 001. It must really be early. I had no idea I was doing the same math problem twice. I haven't forgotten about UR5. 2.89 times 0.000578. There we go. There's like an actual number. 0.0016. All right, I'm just going to leave everything after that off. Okay, well, I have a slight concern that this writing is small enough that when it eventually comes out in a video, it's going to be compressed and illegible. I hope that's not the case. But I got the impression from yesterday that you were all able to read that writing. Just in case it is slightly unclear, those are the numbers that we've got so far. And I kind of worked myself into a corner with R5, but I think I know how to fix that now. First of all, I'm not going to actually use Ohm's law for R5 because I want to show this little shortcut to you. I know that the total voltage is 12. How much is accounted for? I've got 3.9 volts plus, well, this whole thing is 2.89 volts. That's that's 2.89 volts. Okay, so that's only 6.79 volts. How much is left? If you start with 12, and then 3 is gone, 2.89 is gone, how much is left? I'll have to do 12 minus 6.79. 12 minus 6.79, it's 5.21. That's how much is left for that battery. I don't even need to do Ohm's law. 5.21. However, I still will, just to check. Is it true that V equals IR? If I do 4,000 times 0.0013, will I get 5.2? 4,000 times 0.0013. Yep, 5.2. Just making sure that physics works. Okay, and so I got a R, a V, and I. Now all that's left is a P, and that's going to be 5.21 times 0.0013. So, oops. 5.21 times 0.0013. That's it. 0.006773. Ugh. That was just exhilarating. Okay, so see, how long has this been? Okay, so this has been about half an hour, which means I could conceivably do another huge one like this, and everything would be within like a normal 50-minute time span. So what I'd want to do here is just pause and let you respond either with a question in the chat or just a all right, I guess. Just give me a little bit of feedback so that I know that this is either working for you or I can make some adjustment to make it work for you. So go ahead and just drop something in the chat, even if it's just keep doing what you're doing.
Okay, I have a variety of questions.
Okay, hello.
But it's not super about the circuit.
Okay.
I think I know what's going on now, and I'm feeling pretty good about it. That was not the case last week, and I think there's a possibility that like every answer I have turned in a week is like totally wrong.
Oh.
How much is that going to? Not that it's all about the grade, but I am a little worried about it.
Right. So, hey, let's see. Quick before I answer that question, the way that you started that out, you said, I know what's going on now, and it really sounded like you like had some sort of realization that all these conspiracies were true and you could be behind the veil. I was like, oh my gosh, what does she know? Anyway, but so the way that I always try to structure grades with assignments is that when we're learning it, you shouldn't be penalized for not having learned it yet. That's why I've tried to like make a big deal out of that. There's a, you know, test at the end of the week, which basically means I finally want to make something where you have to get it right to get full credit. So pretty much all the work up until now, I'm really just concerned with whether you did it. There's and also, I mean, I'm sure this must have come up in other classes or just occurred to you. There's a certain amount of responsibility that, like, you know, I as your teacher should be taking for how well you're doing. And that means that when, you know, I can't give you instant feedback, or I can't just, like, you know, walk over to your table and like look at what you're doing, that you're, you know, my ability to help you has been throttled, which means that I don't want the consequences of remote learning to show up in your grade. It should really just show up on how long it took us to do this. So if you've been getting stuff wrong for the last week or 2 weeks, like, don't sweat it. It wouldn't have been like that if we were in school, and I don't want the consequences of that to fall on you. So yeah, just if you're gonna focus on getting something right, let's just do that at the end of this week, and yeah, don't sweat everything before. Does that help?
Yes, that does, because it was not for lack of trying, but
Oh,
it was not.
oh, I totally understand that. Yeah.
Clicking like it needs to. And I think I have a grip on it. And you actually talked a little bit about what my next question was, because there's just test on the schedule for like 2 days.
Yeah. So yes. What I'm okay. Yeah. What I want to, what I'm trying to set up is so that let's say I gave you a problem like this. This is more complicated than this. It's not as complicated as let's see, where's that big bad one? There was one, oh, this one. Yeah. It's not as complicated as this one, but then I couldn't possibly give that one to you. That's just too much. So what I'm looking for is some sort of medium difficulty problem so that it would be a fair challenge, if that makes sense. If I just gave you that one's done. If I gave you this one to do, I'm reasonably confident that everyone should be able to do well on it. But you know, I always want you to reach just a little bit past what you're, you know, 100% confident on, just because that makes it like an adequate challenge. So I want you to be able to take your time on it, especially because, you know, the circumstances being what they are. The last thing I want is I'm trying to reduce stress, and so having a medium difficulty problem to do over 2 days. And yeah, I think test was an unfortunate word. I'm sorry about that. Really, just think of it as graded assignment. I think I might, you know, I'm going to have to weight it a little bit more than homework, just because we only have one of them. But, you know, if you think of the weeks of homework that we've had, it's still going to leave you all with like the grade that you came into the fourth quarter with. Try not to make too big of a splash in your grades, because again, there's just not a whole lot of things are so different and unusual that we're trying to not not have like a big mark on your transcript because because of COVID. Oh, I said its name. I think a lot more clearly in the PM, man.
Yeah.
uh,
Okay. Well, I'm feeling like pretty good about all that. Thank you for.
Awesome.
I just like it was a very amorphous test, and I was like, ooh.
yeah, that was my my vague notion of what it would be like on the weekend when I was writing that, and that could use an update. I should replace that with graded assignment. Oh.
It's all good, but I definitely needed the explanation and to see a couple problems. So I appreciate you doing the Zoom.
Well, sure.
But I think I know what's going on. I don't know about everybody else.
Okay.
So.
Well, I mean, if everybody else kind of knows what's going on, then I only need to be here as long as it's helpful to you. So if this is the kind of thing where everyone just kind of like look around at each other, shrug, and be like, all right, I guess, then we can all right, I guess, out of here. But I'm here for you guys. So if either Maddie or Matthew, if they're still here, want me to do something else, hey, just let me know. If there's a particular problem that you're like, I couldn't get that one, or if you're just like, if I saw one more problem, then I'd get it. Just let me know in the chat. All right, that's good. Awesome. And I haven't seeing exclamation points like that had more of an effect on me than I expected. That actually makes me feel really good. Awesome. How about you, Matthew? Don't worry if you're the only one who wants to see something. I'll do it for you. Okay. Awesome. Well, let me know which one it is. Was it one of the ones that I have on this screen in these tabs? Yeah. I feel like I'm going through like a suspect lineup at the police station. Is it equation? Let's see. This one's the big long one. Okay. So this is form 3. This is form 2. That's form 1. I have them out of order. This is. I don't have the name on that. Let's see. Keep going. Big long one. I think that's the last one. Form 1. Okay. So let me go back to form 1. Okay. Yeah, this one. I could see how that one might be confusing. Is this the one, Matthew? Awesome. Okay. Let's do that. Okay. So this is just about equivalent resistance. We don't need to bother with Ohm's law and V and I and R and all that. It's just resistance. So, all right. So I'm gonna be using my super sophisticated Post-it note special effects again. And so what I would want to do is investigate the structure, the connectedness of this circuit by redrawing it and seeing whether it's equivalent. So here is alternative number 1. Let's see if this is the same circuit. Okay, so this is an alternate version. The question is this the same circuit as this one? Well, let's just look at these two and see if it's the same path or the same paths. So you come out of R1 and you come to a fork. Come out of R1, you come to a fork. If you turn right on that fork, you go through R2 and then you're out. If you turn right through R2, I'm sorry, if you turn right, you go through R2 and then you're out. However, if you go straight, you gotta go through R3 and R4 and then you're out. If you go straight, you gotta go through R3 and R4 and then you're out. Well, yep, these are the same circuit. So does this one look a lot easier to you, Matthew, than this one? I don't know about you, but that one makes a bit more sense. And that one actually is similar to this because I've got two in series in parallel with a third one. Well, that's just two in series parallel with the third one. So just, trying to show my train of thought here. If I start with this resistor, start with this circuit and slap this one here to show an equivalence. Hold on, I got more post-it notes. Cool. Now R3 and R4, that I can replace with something. So it looks like R3 is 10.7 thousand and R4 is 870. And they are in series. So let me add those. 10,700 plus 870, 11,570. So I could actually take R3 and R4 and replace them. Production budget on this video is through the roof. You get the idea? That this 11,570 ohm resistor is actually just those two that are in series. So this parallel group represents the entire rest of that circuit. So this is as best as I can, visualize how I'm digesting the circuit. So R2 and this one are in parallel. Let's see, what was R2? Should have written it down. R2 was 7.6 thousand. So just real quick, 1 over 7,600 plus 1 over 11,570. Calculator. Oh no, I closed it. Oh, dang it. That was it's like the equivalent of dropping my calculator while I was using it. So 1 over 7,600 plus 1 over 11,570. Hey, yeah, 458. I'm just going to call it 4587. So my very last special effect this whole thing gets replaced by this. And then you just have to add it to R1. Okay, so just to unpeel that, and now that should answer your question. This circuit is the equivalent of those two resistors, but this one is the equivalent of those two, and this is just an easier way to do that. Ta-da! All right, does that answer your question, Matthew? I probably answered it 5 minutes ago, and I was just keep going. I just kept going. Man, if there is one thing that I miss, so I know I'm actually doing it right now, but there's this thing that you know, science nerd people do, and I'm sure you know this. We tend to go on and on, and I've learned over time to recognize boredom in faces so that I can learn it's time to stop talking. That's something I don't get anymore, so I have to try and catch myself. Anyway, it sounds like I've done what everybody's wanted. It's also been 50 minutes, so unless you have something else, I think we can call it a day. As soon as this recording processes, I'll post it to YouTube so everybody can enjoy it. Otherwise, you're welcome.